everybody, it's Mrs. Hofferberth. Let's talk about entropy today. Entropy is defined as a measure of the dispersal of matter and energy. Mathematically, we use the expression big S, which is the symbol for entropy, is equal to K, which is the Boltzmann constant, multiplied by the natural log of W, which is the number of microstates available to the system. A microstate is a way you can arrange your particles. So if you think of watching a system, maybe a gas, as it moves in a container, all the different possible ways that that gas might be arranged as those particles bounce around, every little snapshot, those are all a microstate. If your goal is to increase the entropy of a system, then you just need to have more microstates available. So as the number of possible arrangements of atoms or particles increase, then your entropy is also going to increase. Now, there's a couple different ways that you can accomplish increasing your entropy. You can do so through the dispersal of matter or the dispersal of energy. So when you talk about the dispersal of matter, there's a couple of possibilities. One, if you have a gas and you provide it more volume to occupy, there's a lot more places those particles can be. Many more microstates, your entropy increases. Phase change can also have a huge impact on the entropy of a system. If you think of a solid, those particles are really locked in place and they're vibrating. There's some vibrational motion, but they can't move very much. Once you turn something into a liquid, now they're starting to be able to move. They can have rotational motion and translational motion in addition to that vibrational motion. So with that greater amount of motion available, you're going to have a much greater entropy. You can also just have more particles. So if you look at stoichiometry during a chemical process, if you end up making more particles, now you have more things that you can arrange, and there are more possible ways to arrange them. So having more particles will also increase your entropy. It's worth noting that the impact of the number of particles is especially important when it comes to gases. Because those particles are moving so much more and already have a higher entropy, having more moles of gas has a huge impact on your entropy for the system. You can also increase the entropy or change the entropy of a system by changing temperature. If you increase the temperature, you're increasing the average kinetic energy of your particles. And if you look at what's called a Boltzmann distribution, I'm going to draw one. What you find is that at low temperature, the particles have a low average kinetic energy. And so what you'll see is a relatively tight arrangement of molecules or particles with a particular kinetic energy. And so the average kinetic energy is fairly low. However, when you increase the temperature, then your average is going to increase, but you're also going to have many more possible kinetic energies that can be accessible to those particles. And so you see a broadening of the curve. This does result in a higher average kinetic energy, which is that definition of temperature. But because there are so many different temperatures that now can be accessed by the system, you have far more microstates available. So if you increase your temperature, you're going to increase the entropy of the system. You need to be able to look at a system or a couple of systems and decide qualitatively which has greater entropy. So for example, if I have 10 grams of ice and 10 grams of water, same amount of particles, but the water is going to have a much higher entropy. Those particles are much more able to move, and so there's far more microstates available to them, and thus the entropy increases. The second example I have drawn is for the chemical reaction of two nitrogen monoxides reacting with an oxygen to form two nitrogen dioxides. Here, everything's a gas, so there's no phase change involved like there was in the previous one. But if you count, there are 3 moles of gas on the reactant side and only 2 on the product side. As a result, the side of the reaction, the reactants, will have a higher entropy because there are more particles. Thus, there are more ways to arrange the system and a higher entropy. Finally, if you actually look at 2 different molecules, the entropy is going to be increased by how many ways that particle itself can be arranged. So methane, 1 carbon and 4 hydrogens, versus propane, C3H8. The propane will have higher entropy because there are more particles within the molecule, which provides more different ways for those particles to move, for those atoms to move relative to one another. We say that propane has a greater number of degrees of freedom available to it, and thus it will have the higher entropy. In general, increasing molecular weight increases your entropy. Increasing molecular flexibility also will increase your entropy. Let's return to theory for just a moment. The first law of thermodynamics was conservation of energy. The third law of thermodynamics says that the entropy of a pure crystalline substance will be zero at absolute zero. So let's figure out what this means. In order to have an entropy of zero, since entropy is S equals K ln of W, to have an entropy of zero, you need to have 1 microstate, because the natural log of 1 is 0. And so in a pure crystalline substance, every particle is identical. They are going to be located exactly in the crystal lattice locations, so the location of every particle is set. And if you get to absolute zero, the particles stop moving. And so that takes that whole section. There's no vibration, there's no motion. That takes all of that out. So in a pure crystalline substance at absolute zero, there is only 1 microstate. This is more of a theoretical aspect rather than being practical, because we don't live at absolute zero. But it does mean that we have something to compare all of our entropy values to. So unlike enthalpy, where your values were relative to the elements in their most stable state, that was kind of a default designation. Here we have something where we can say this is zero. And so we actually have what are called absolute entropies. Every other entropy for your compounds and elements is relative to what that zero would be. And so our entropies are absolute. From a practical standpoint, we'll typically talk about standard molar entropy, which is the symbol S0. So standard state typically refers to 1 atmosphere of pressure. At least historically, that's kind of been the fact. And it's still pretty close to what we're using currently. So we're going to go with 1 atmosphere of pressure for any gases that we happen to have. And these values are tabulated. And so there is an appendix in your textbook. It is Appendix C, and it has values for delta H. You've actually used it before. For delta S, and for something called delta G that we'll meet shortly. But there are values that have been measured for a whole host of different elements and compounds. So use Appendix C to find your standard molar entropy values. And while it's great to talk about the entropy of a particular item, of a particular compound, more often than not what we're interested in is how entropy changes throughout a chemical reaction. Again, you should be able to predict it qualitatively, but we also want numbers. And so the best way to do this is an equation that is analogous to one you saw for delta H, and that is delta S naught. So we're going to work with standard values here. Delta S naught equals the sum of the entropies of the products minus the sum of the entropies of the reactants. You do need to take into account the number of moles of each reactant or product that you have. But like I said, it's exactly like we did for delta H, and it's a nice, easy way to calculate the change in entropy during a chemical reaction. So in sum, entropy is a measure of the number of available microstates in a particular system. It is 0 for a perfect crystalline solid at absolute 0. That's the third law of thermodynamics. We have tabulated values for the absolute entropies for a whole variety of substances. And you can use the equation delta S naught is equal to the sum of the entropies of products minus the sum of the reactants in order to calculate delta S for a chemical process.